Okay, so tutorial 6 is an interesting little tutorial. I think it'll be quite short. Influence lines are, well, they're interesting, but with Moeller-Breslau, they're extremely short and pretty easy to do. So once you understand Moeller-Breslau, and that's basically what I'll be going over, I do not really like doing influence lines by equations. And you'll find actually that if you actually go out into industry, that you usually don't. Moeller-Breslau is usually adequate enough. Basically, you're only using Moeller-Breslau to determine where the maximum load could be placed. You don't really care about the actual value of the load. So if you can get the shape, you'll be in good hands. So just a brief overview rather than going into a specific question just yet. If you have, what do you have? If you want to find, let's say that you have simply supported beam for now. If you want to find the reaction, you remove the ability to resist force here. So if we remove the ability for this to resist force, this tip will rise. Right, basically what we would have is something like this. Right, and we're now going to raise that up by some unit 1. Then we'll draw in our little reaction. So this is the unit influence line for reactions. So for reactions, I have something like this, and let's call this A and B. Yeah, and I'll put some point C here. This is not a hinge. This is just a reference point at L/2. So if we want to find a reaction, we just lift the point up. This becomes our unit influence line for our reaction. And this should make sense, right? If I put a load right at A, all the force goes directly into A. That's why we have the maximum here. If I put a unit load of 1 at B, all the load will go into B. I'll have no reaction at A. So this is reaction at A. I should have clarified that earlier. This is RAY. So that's fairly straightforward. Next one is shear. Shear is an interesting little case. Let's find the shear at. We can really do any of them, I guess, but let's find the shear at C. If I want to find the shear at C, I remove the ability for this to resist shear. So I literally cut it right at C. I cut it at C. And do you remember what our arrows look like? This is what our arrows look like for shear. This is the positive shear convention. I think that's the positive shear convention. So I'm going to lower this point down by some amount, and I'm going to raise this point up by some amount. And the amount that the separation between these 2 points will be 1. But that does not necessarily mean that it is 0.5 above and 0.5 below the axis. In addition to the displacement between these 2 points being 1, the 2 slopes have to be parallel. The 2 lines have to be parallel. So I'm going to have something that looks like this, where the displacement between here is 1. What do I mean by they have to be parallel? Basically, if we were to look at another case, right now I'm assuming this is L on 2, L on 2. What if I have a case where I'm interested in the shear at some point where L equals 4, or where we have C at L equals 4. So for example, if I had something like this, I cut it like this. Let's assume this is drawn to scale. If I cut it like this, I'm going to want the separation between these 2 points to be 1, and I want the slopes to be parallel. So this will go 0.25 below the axis and 0.75 above the axis. Note that this is still 1, but now these two lines are parallel, and now these two lines are parallel, so this did not go 0.5 below the axis. This was 0.5 and 0.5. This is not. Finally, let's look into moments. Moment, I think, is going to be the most confusing case, because he keeps saying we rotate it by 1, and I think a lot of you are going like, well, what the hell does that actually mean? So when you bend something, let's do the simple case, we're bending it right in the middle, L on 2, L on 2. I'm going to put a 45-degree angle on it. In other words, I'm going to want, if I draw this correctly, this to be 45 degrees. That's one way of looking at it. But I can also just say that this is going to be sum theta equals 1. What happens for 45 degrees? What is a 45-degree triangle? It is where this is 1, 1 root 2. This is what he means by theta equals 1. He means your rise is the same as your run. You come back over here by geometry. I'm not going to derive this for you, but this will be theta on 2. If this whole thing here is theta, this will be theta on 2 on each side. These two angles will add up to this 45-degree angle. So you might be asking, like, well, how do I use this later? You need to know this information in order to get the height of this on the moment diagram. This is L on 2 and this is L on 2. The height of this will just be 1/2 times L on 2. I took the coefficient of theta, I multiplied it by the length, and that gave me my height. Let's do another example. If I want to find the moment here, and this is L on 3, and this is 2L on 3, I'm going to get some deflected shape, and I'm going to get some shape that looks like this. I'm going to get some shape that looks like that. This angle will be 45 degrees. And this will be theta equals theta equals 1. This angle is going to be 2/3 theta. This angle will be theta on 3. This angle is 1/3 of the base. This angle is 2/3. Sorry, this angle, this coefficient and this coefficient will be the same. This coefficient and this coefficient will be the same. If I look at a different, so then the height of this, what will the height of this be? The height of this will be 2 on 3 times L on 3 equals 2L on 9. And if you want to prove this is very easy to prove. Just draw your normal moment diagram. Put a unit load of 1 here. Say this is L on 3, this is 2L on 3. I really need to get a bigger desk. This is very unfortunate. L on 3, 2L on 3. The reaction here will be 2/3. The reaction here will be 1/3. My moment at this point will therefore be 2/3 times L on 3. Right? I have force here, force here. The moment here is this force times this distance 2L on 9. So I get the same thing as I would expect. So that is your moment. So one of the things that you must make sure you do, and I think the professor stressed this quite often in class, is that you must maintain boundary conditions. So up here I raised the reaction by 1, but I left the deflection at the other ends by 0. I'm obeying this reaction. I'm obeying the boundary conditions here. The displacement here must be 0. Over here I separated these 2 points by 1, but I'm still obeying the boundary conditions. My displacements at either end are 0. It's free to rotate, but the displacements must be 0. Same thing over here. I bent my beam by 1, by some unit 1. My rotations, I'm free to rotate, but my displacements must be 0. If you look at a cantilever case, cantilever goes out like this. Let me just draw several cantilevers right now, actually. If I want to find the reaction at the cantilever, I literally raise the cantilever up by some unit. There we go. I have to maintain this boundary condition. This is my new unit influence line. I have to maintain this boundary condition, so the slope here is 0, and the slope is 0 all the way across. Over here, I raised the reaction, but the slope changed because a pin and a roller are free to rotate. If I want to find the shear, my shear actually looks quite a bit. You can imagine that for the cantilever, I also have some bit that goes this way. That goes into the cantilever. This will make more sense later. I'm cutting it here. If I want to find a shear at the reaction at the cantilever, I'm cutting it here. I'm raising this section up by 1. This must be parallel to this. And the displacement between these 2 points is 1. So this is exactly like we had before. Finally, if I'm interested in the moment, I'm going to put a unit rotation here of 1. So basically the angle between this and this is 1. You can think of it like 45 degrees. Now it's not exactly 45 degrees because just because of the way these things work. Like theta, when we say theta over 2, it's not literally going to be 45 over 2. It is not going to be that. But this will give you, well, I don't think it will be, but it should give you a good approximation for what we're doing. I think that's everything. I drew one too many examples, but yeah, so that is influence lines in a nutshell, pretty much. I don't really want to go over problem. This is basically the video for problem 1. Just because of the way problem 1 is structured, it's very hard for me to actually do one of these without giving you a solution, and I think you need a lot of practice with influence lines. So I'm not going to go into any of these examples. Just for 1A, it doesn't ask you to do this, but you'll need this later on, so do it anyway. Also find the bending moment at A. So also find the bending moment here. You need this for question 2. Other than that, let us know if you have any questions.